Now we're still going to be talking about graphing here, except we're going to move on from x-intercepts and y-intercepts to symmetry. And there's three types of symmetry we can talk about. So we have three types of symmetry. We have one, symmetry with respect to the x-axis. Symmetry with respect to the y-axis. And then symmetry with respect to the origin. I'm going to first just sketch some graphs here, and then we'll go ahead and do the actual definitions and look at some examples. So I'm going to do 3 sketches. So the first sketch here this is x-axis symmetry. And x-axis symmetry, the reason this is x-axis, is you can imagine if you were to take either one of these pieces, so let's take, highlight this piece here in red here, so let's take this piece right here, and let's flip this over the x-axis. If I take this and flip this over the x-axis, where does this line? It lines exactly up here. In other words, if you take this graph and flip it across the x-axis, you get the exact same graph. With that in mind, you can kind of maybe guess what y-axis symmetry is going to look like. Y-axis symmetry would look like something like this. Where this is y-axis. And we can clearly see if we do the same thing here as we did in the previous problem, instead of flipping it across the x-axis, we flip it across the y-axis here, we would get the same graph. And one last one here, which is the origin. This one's not as straightforward to see, but there is an easy enough example we can sketch. This would be symmetry, well, not quite. Let me get a better sketch here. That's a little bit better. This would be symmetry about the origin. And what you want to think about this is you have to flip over both the y and x axis in order to get the symmetry. So this is origin. So how do we test for symmetry? I mean, we can look at a graph and determine whether it's symmetric about one particular axis, but what about if we don't have the graph? If we just have the equation of the graph, how can we test for symmetry that way? Well, let's go ahead and review this here, or talk about it. So if we have x-axis symmetry, well, the definition means that if xy is on the graph, then so is x negative y. So to test, substitute negative y into equation and see if you get the same thing. And what I mean by that, see if the equation remains the same. Then we have y-axis symmetry. And this is if xy is on the graph, so is negative x y. And then the test for this one, substitute negative x into the equation and see if the equation remains the same. And then origin symmetry. If xy is on the graph, so is negative x negative y. And then again, to test for this, substitute, in this case, negative x and negative y into the equation. And see if it remains the same. Alright, so let's look at a couple examples of this, of testing for symmetry. So let's go ahead and start with a couple straightforward ones here. We're going to test for all the symmetry. Now, we're going to do all three tests for symmetry, but it turns out you can only have one of them. You can't be both x symmetry, well, typically you're not both x and y symmetry, although it is possible. Typically we're not going to be encountering equations like that. So typically you only have one symmetry present, but you should always check to make sure all of the other ones aren't present. So let's look at an example here. So test for symmetry. Test for all three symmetries. And we're going to have x squared minus y equals 0. Now, the important thing here is this is the equation right here, this one that we wrote down, is what we're going to have to always go back and check to see if you get the same thing. Alright, well, let's go ahead and do x-axis first. So x-axis, remember we substitute negative y in. So you'd have x squared minus negative y equals 0. And then you simplify it. And so if we simplify it, we have x squared plus y equals 0. Now we need to compare it to our original equation. So we need to compare it to this equation here and say, is this equation that we wound up with exactly the same? And of course, really quickly we can see it's not. Notice that you have a plus here, and then up here, of course, we had just a minus. So it's not the exact same equation. So what does that mean? that means there is no x-axis symmetry. Now let's test the other ones. We have y-axis symmetry. So y-axis, what do? Is we substitute negative x in. So you have negative x quantity squared minus y equals 0. Now we have to simplify this out. So again, this is y-axis. So negative x quantity squared, well, the negative gets squared, which if you square a negative, that becomes positive. So simplifying this gets me x squared minus y equals 0. And I'll scroll back up a little bit here, and we can see that's exactly the same as the equation I had. So what this means is we have y-axis symmetry. And then we have one more test to do, and that's for origin. Well, for origin symmetry, we've got to substitute both negative x in. So I have negative x quantity squared and negative y in. And then if we simplify this, we have x squared plus y equals 0, which has the same problem as we did one of our earlier tests, is I have a plus here instead of what should be a minus. And so then what this means is I have no origin symmetry. All right, let's look at one more quick example here for symmetry, testing all the cases. Let's look at, so test for all three symmetries. xy equals 4. All right, so we're going to test for all of the symmetries here. Let's go ahead and first do x-axis. So what do we do for x-axis? We substitute negative y in. So I have x times negative y equals 4, which of course is negative xy equals 4. And I'll just circle it here. I've got a negative sitting out there now, which of course means it's not exactly the same. So this is no x-axis symmetry. Y-axis. Okay, well, let's do another test. Test for y-axis is we put negative x in. And so this would again just be negative xy equals 4. Same reason as above. I won't even bother circling it this time. We have no x-axis symmetry. One more to go, which is of course origin. And origin, we substitute both negative x in and negative y. Well, negative x times negative y, two negatives give me a positive, so I actually wind up with simplified. This is x times y equals 4, which if I scroll back up here, is the original equation. Exactly. So that means I have origin symmetry. Now, these examples all had symmetry, but I want to emphasize equations don't have to have symmetry. And an easy way to see that is just look at this example here. Y equals 3x plus 1. there's two ways you could do that. You could actually sketch the graph of this and see that there's none of the symmetries present, but you can also go through the tests. I'm not going to go through the tests. I'm going to leave that as an exercise for you, but if you go through all the tests here, you should get no symmetry. You won't have x-axis, you won't have y-axis, and you won't have origin symmetry.